All right, in this video, I'm going to be telling you about matrix arithmetic. So we're going to do some addition, we're going to do some multiplication, we may find some inverses. All right, so let's start with, what is... All right, so when I say an m by n matrix, I mean a matrix that has m rows and n columns. Okay, now I don't assume you know very much about matrices, except for maybe that it's a box that numbers go in, right? So what I'm going to say is that this matrix M right here is a 3-row, 4-column, 3 by 4 matrix. Okay. Now, next I'm going to define something else for you. And that's or n by n. Now this is something that in maybe a more serious linear algebra course they might you might do some investigation of different spaces, like spaces where you could take matrices and put things other than real numbers in them. For now, really what I'm going to say is that if I say M is an element of R 3 by 4, that just means it's a 3 by 4 matrix in this class. Okay, so I would say M is an element of R 3 by 4. Now next, we're going to need kind of a way to talk about a particular entry within our matrix. And so I'm going to, say the ijth entry in... I kind of forgot what I said before I paused the recording to write this down, but and you can see the grid lines, but that's going to be all right. Let's get rid of those. All right. And the ijth entry of A is the entry on the ith row and jth column of the matrix. So for example, M2, 4 is the entry on the second row and fourth column, which is going to be, right here. Okay. And that means that M sub 2, 4 is going to be 9. Okay. And that'll be something that'll be nice for us, or at least for me to describe to you how are we going to add two matrices. All right, so let's do that. So if I add in a new matrix P over there, I'm going to tell you matrix addition, it works exactly like you think. So, but this, and I'm not going to prove this for you in this video. It would be really tedious. If you're really interested, you could do it yourself. I don't think it would, maybe this is a definition. I don't even know. Regardless, what I'll tell you is that the ijth entry of matrix A plus B is going to be equal to the ijth entry of A plus the ijth entry of B. Okay. So that means that, for example, M plus P is the matrix that we get by just, adding the corresponding components together. 1, 2, 3, so 1, 2, and I'll add a 4. Okay, so 1, negative 1, 0, 3, negative 1, 0, and 0, 0, 1. And that's how we add matrices. It works exactly like you expect. Now, for K being like some kind of constant, like a real number, if we have a matrix A and we multiply it by a constant, that also works like we expect. So what I'm going to do, I might even start before I write down the rule and talk about, 2p. 2p, we're just going to double all the entries of p. Negative 2, negative 2, negative 16, negative 18, and negative 20. Okay, so we'll say that the ijth entry of matrix, A multiplied by constant k is, well, that's just going to be k times the ijth entry of I, or the ijth entry of A, pardon me. We just take the 2 and we distribute it to every entry in the matrix. Okay. So that's equal to k times the ijth entry of I. Okay. and that's multiplication or scalar multiplication and addition. Okay, so let's look at some matrix multiplication now. The matrix product A times B exists if the number of columns of A equals the number of rows of B. Okay, so what I'll tell you is we're not going to be able to multiply M by P or P by M, right? That's not going to be possible. Okay, it's not going to be defined. Okay, for example, if Q is a, what do I say, a 4 by 5 matrix, and T is a 3 by 3 matrix, then, for example, I'm going to talk about MQ, MT, and TM. And what I think I want you to do for this, yeah, I think this is good, is M is a 3 by 4. And so what you do is you kind of copy the dimensions of M right below it. And then we're going to copy the dimensions of Q right below that. Now, since we write it rows by columns, and the columns of the one on the left needs to equal the number of rows on the one on the right, if these two numbers are the same, then the product is well defined. Okay. Also, just something I'm going to throw out there, the dimensions of the product are the other two numbers. So MQ is a 3 by 5 matrix. T, well, let's say M is 3 by 4, and T is 3 by 3. Well, notice that 4 and 3, these are not the same number, right? That's not good. Okay, so I'm going to say that this product is undefined. Okay, and then TM, T is a 3 by 3, and M is a 3 by 4. Okay, again, the same number, I'm good to go. I'm going to say that the product TM is a matrix, and it's going to be a 3 by 4 matrix. Right, now, rather than, giving you an actual formula for the matrix product, or really the ijth entry of the matrix product, I'm going to just show you how it's done. And then I'm going to tell you that in order to really get good at this, you got to just repeatedly practice this yourself, okay? So I'm going to start off by computing, I'm going to show you how to compute the product mx, okay? And then I'll do m times a bigger matrix than x. And then I think that'll be all for matrix multiplication, because again, the only way to really get this is by just practicing it yourself. All right, so let's just copy the problem fresh so I have enough room to write and annotate this 0, -1, 0, 401. I probably should have copied this while I was pausing recording, but whatever. 8, 9, 1. Okay, we're going to take this, and we're going to multiply it by the vector 1, 0, 1, 2. All right, and so what we're going to do is we're going to kind of make something that I always have said, it looks like a 7, right? And by 7, I mean that. Okay. So we're going to choose the first row and first column. Okay, you kind of make a 7. Row over here, column there. And then we do something that feels very much like taking a dot product. Okay. So I'm going to do 1 times 1 plus 0 times 0 plus 4 times 1 plus 8 times 2. Okay. Can go through that arithmetic, but I've got 16 and 4 is 20 and 1 is 21. Okay, that's how I got the first entry, by going off of the first row in the first column. Okay. Now, next I'm going to go down here and also against that column. And since I went down from the first row to the second, I'm going to go down in my product when I compute this dot product feeling thing. So I got 2 times 1 plus -1 times 0 plus 0 times 1 plus 9 times 2. I feel like that's 18 plus 2 more is 20. And now if I'm going to move down once more, Okay, I'm going to move down in my product. I'm going to do the same dot product feeling thing. So it'll be 3 plus 0 plus 1 is 4. Wait. 3, 0, 1, 1. Oh, no, this was an 11, right? Yeah, I was going to say, I don't remember the number ever being that small. Okay, so 3 plus 0 plus 1 is 4, and 22 is 26. Okay, so that's mx. Okay. Now you might be like, okay, you multiplied a matrix by a vector, like, but can you show me like some bigger multiplication? And I suppose I could. I think what I'm going to do is I'm going to say, I'm going to talk about, maybe I'll rename this y, call it it's a matrix now, and I'm going to just, add on a little column to it. So if I now am interested in multiplying the product my, that's 0, 1. If you think about it, kind of working the same process as before, if you're setting up your 7 and you go this by that one, right? And then you move it down, and then you move it down again, that's not really going to change the result, at least when you're working against the first column. But then, when you shift this over to the right, well, we're going to need to shift over to the right in our product. So I'll be over here. I'll be just dotting now this with that. This row, first row with the second column. And, hold on. Oh, yeah, it's going to be 8. Pardon me. I'll call it 8. Second row down here. I'll do the dot product. I'll end up with 9. Then I will move that down once more, and I will get 11. Okay. So it's a lot of dot products, a lot of just making sure you're setting up the right row by column. And if you're really curious, all right, that's the full-blown proper definition of the ijth entry of the matrix product AB, but don't feel like you need to know this, right? This is just only if you are interested in the technical definition. All right, next I want to talk to you about transpose. Oftentimes I forget to mention this until it's too late, and I've asked you a question about transpose or something, and you're asking me, like, what is that exponent t there? So let me tell you, transpose is basically where we're going to take the matrix and turn it sideways or something. I think some people have seen this before, some people might not have. Again, I don't assume anything, so I'm going to just tell you the definition. So if A is an m by n matrix, then A transpose is an n by m matrix. And okay, you can look at the ijth entry definition, but what I'll tell you, the best way to think about this is that the rows become columns and columns become rows, right? So I'm going to say that m transpose is going to be, well, I'm just going to take the rows and make them columns. 1048, 2, negative 109, and 30111. That's m transpose. Now that I've done that, you might want to stop and check and make sure that what had been columns are now rows, right? I took rows and made them columns. So 1, 2, 3, I see that as a row. 0, negative 1, 0, yes. 4, 0, 1, 8, 9, 11. These are my rows. Okay, that's how we take a transpose. Okay, that'll be something that we'll need later on in the course. Next, I want to tell you a little bit about identity matrices. So I2, which is 1, 0, 0, 1, is the 2 by 2 identity matrix. Okay, a fact is that, if, let's just say A is a 2 by 2 matrix. But this is true in general. A times I2 is always equal to A. It's like multiplying by 1. It doesn't change the matrix. Okay, if A is a 2 by 2 matrix, then we can do both of these products. And again, both of these will be A, right? Now, I need to tell you that that I3 is a 3 by 3 identity matrix. 0, 1, 0, 0, 0, 1, okay, is the 3 by 3 identity matrix. Okay, what I need you to know about just identity matrices of any size is that along the main diagonal, which is what I'm highlighting here in yellow, that entry is 1, everything else is 0. Okay, that's an identity matrix. That same thing. It's like multiplying by 1, provided the multiplication is well defined. Okay, so I need to tell you about the identity matrix so that I can tell you about the definition of the inverse matrix. Now, today in class, I had someone come up to me afterwards and be like, hey, you showed me how to add, multiply, and subtract matrices. Can you divide them? I was like, oh, yeah, I forgot to mention that. I usually would not only show you about, the nature of an inverse, but also how to find the inverse for a 2 by 2. I just completely forgot to do that in one of my sections. But that's okay, because I'm going to show you now. Okay, A inverse is, we can only compute the inverse of a square matrix. That's what I'm saying, n by n. And now this might be a lie. This is a maybe is an element of. Okay, if it's defined. Not every matrix will be invertible, as we'll see later on in the course. If the inverse is defined, it's the same shape, it's n by n, and when we multiply, a by a inverse or a inverse by a, we get the identity back. Now, let's see. Yep. Okay, so now I need to I'm going to wrap up with a couple of special facts about 2 by 2 matrices. First thing is that, at this point, you're just going to have to take this on faith. If A is equal to matrix A, B, C, D, then determinant of A, which we don't really have any meaning for besides I'm just going to tell you some things about it. The determinant of A is going to be AD minus BC. Okay. And also, and this, we might also write the determinant of A using vertical bars around the outside of the matrix, so A, B, C, D, and maybe you remember that from something else we've done in this class. Okay, and that also involves this, fish-looking thing, but, leave that for you to think of. Okay, so I've defined the determinant, and then I also need to just tell you how to find A inverse. One over the determinant of A multiplied n on, we switch these two, right, D and A, and then we make these two negative. So negative B, negative C. And so, I could, write determinant of A is AD minus BC and, distribute that in and put 4 things that would all be fractions. That would just kind of be a lot. Now, you'll see just right off the bat, I think, that right here, if determinant of A equals 0, then matrix A inverse is undefined. And we'll see why that's true, pretty extensively throughout the course. Okay. But I think that's all I got for you for this video.